All right, hello everyone, and welcome to our very first lesson of Unit 4, which is on chemical reactions. Today we are going into an introduction for chemical reactions, specifically focusing on physical versus chemical changes. So our goal for today is to be able to identify evidence of both kinds of changes in matter. A physical change is not going to alter what the substance is made of, it's just going to change how it looks or behaves. And a chemical change is going to change the substance's composition. So you'll know a chemical change has occurred if you see heat or light being produced, a gas forming, a color change, or a solid precipitate appearing. These signs all indicate that the atoms have been rearranged and that a new substance has been formed. A physical change is when a substance changes how it looks or what state it's in, but it's still the same substance chemically. For example, when we melt, freeze, or boil water, all it's doing is changing the phase, so solid to liquid to gas. It doesn't actually change what the substance is made up of, which is water. Mixing and then separating substances or dissolving something in water also counts as physical because you can usually get the original substance back. In a physical change, no new substance is created and no chemical bonds are made or broken. The color, shape, or density might change, but the actual chemical makeup does not. This is why breaking glass or melting ice, that's going to be physical and not chemical. A chemical change is one or more substances that are converted into entirely new substances with new chemical composition. In other words, the atoms are rearranged and new bonds are formed and or broken. There are several clues that tell us whether a chemical change has occurred or not. If you see a color change that isn't caused by lighting or dilution, that's a sign that your new substance is forming. Gas production like bubbling, fizzing, an odor, or smoke is another strong indicator. You might also notice a precipitate, which is a solid that appears when two solutions react with one another. And additionally, a temperature change or the release of light or heat means energy is being transferred during the reaction. So unlike physical changes, chemical changes are usually irreversible under normal conditions because new substances are formed. So dissolving a salt is one of those things in the chemistry community where people kind of argue whether it's physical or chemical. And in reality, it can be either or depending on what salt you're dissolving. So if we're talking about something like sodium chloride, which we work with a lot in AP chemistry, if we're dissolving sodium chloride in water, the composition of Na and Cl in the ionic compound is not actually changing. It's just those ions are now free floating instead of in an ionic crystal lattice. So no new substances are formed, and the process is reversible, which means we can evaporate the water and we can get that sodium chloride solid back, which means that if we're talking about dissolving sodium chloride in water, this would be considered a physical change. Now, just because we have an ionic compound dissolved in water doesn't mean it's always going to be a physical change. Sometimes we have ionic compounds that when dissociated in water, they actually form new products, which would then be a chemical change. So let's compare what we talked about last slide, which is sodium chloride, with our example on this slide, which is iron 3 chloride. Now, both of these ionic compounds, when we dissolve them in water, the first thing that happens is they dissociate into their individual constituent ions. So for sodium chloride, we have Na plus ions and Cl minus ions. And then for our iron 3 chloride, we have iron 3 plus and we have Cl minus ions. Now you can see here the main difference between these two is that Fe3 plus has a much greater magnitude of charge. And we know with Coulomb's law, the higher the magnitude of charge, the more attraction it's going to have for something that has a negative and positive end. So for water, if we're looking at these iron 3 plus ions attracting to water molecules, we know they would be attracted to the oxygen side, which is negative. This intense force, because it has such a strong magnitude of charge, is going to distort the O to H bonds in water molecules, which pulls on the electrons so much that the hydrogen ions are released. So now we are left with these iron ions attracted to the negative hydroxide ions, and then our chlorine anions attracted to the H plus ions, which is where we get our FeOH3 and our HCl. So through the lens of Coulomb's law, the difference comes down to the charge strength. So the greater the ionic charge, the greater the attraction to water molecules, and the greater the chance of a chemical reaction instead of just a physical change. A physical change usually involves breaking or moving around or changing intermolecular forces, which means the change that happens between molecules and not inside them. A great example of this is a phase change, like when ice melts into liquid water or when water boils into steam. Each of these phases, the actual water molecules stay the same, but the hydrogen bonds between them are what change. In solid ice, there are more hydrogen bonds holding the molecules in a fixed structure, and as that ice melts, some of those hydrogen bonds break, allowing the molecules to move more freely in the liquid state. And then when water turns into vapor, almost all of those intermolecular bonds are broken. So even though the state and the spacing of the molecules change, the chemical structure of each water molecule does not, which is why this is a physical change. Chemical changes, unlike physical ones, involve the breaking or forming of intramolecular bonds, which is the bonds within a molecule. During a chemical reaction, these bonds are either broken or formed, which leads to a creation of an entirely new substance. In the reaction shown here, we have magnesium metal reacting with diatomic oxygen gas, and it forms magnesium oxide. So on the left in our reactant side, we can see that we have a covalent bond between the two oxygen atoms. And in order to form magnesium oxide, that covalent bond has to be broken, which means energy has to be put into that molecule in order to break those bonds. Then when those bonds are broken, we end up creating an ionic compound of magnesium oxide. And these green lines here are actually just showing you that it's a new type of bond, which is ionic. I don't want you to get confused because we do not show ionic compounds like this when we're drawing them out. If you were ever to draw them out specifically in a particle diagram or something like that, you would write something along the lines of Mg2 plus next to O2 minus or something like that. But overall, this process is showing how atoms can rearrange to create new compounds with new properties and new types of bonds. And because that internal bonding structure is changing, this is why it is considered a chemical change. So I know you've already learned this in the past, but I did want to go over it quickly just in case we did not know it or needed a brief reintroduction to it. Remember, when we are doing chemical reactions, we show them using chemical equations. The reactants are on the left, the products are on the right. The large numbers to the left of substances are going to be called your coefficients, and the small numbers to the right of atoms are called your subscripts. These are the 5 main types of chemical reactions that you should recognize in this point of AP Chemistry. The synthesis reaction is going to combine 2 or more reactants to form a single product, whereas a decomposition is the opposite of this. It's going to take a single reactant and break it down into 2 or more products. Then we have a combustion reaction. Typically, these are going to involve an organic molecule reacting with oxygen gas to form carbon dioxide and water. So we typically have our hydrocarbon reacting with oxygen gas to form carbon dioxide and water. Then we have our single and double replacement reactions. Single replacement reactions occur when an ionic compound reacts with an element to form a new ionic compound and a new single element. And then a double replacement reaction occurs when you have two ionic compounds and they're essentially going to switch partners. So a single replacement reaction could be something like sodium chloride reacting with magnesium. And so then you will get magnesium chloride and sodium. And then our double replacement reactions involve two ionic compounds. So let's say we had sodium chloride and magnesium oxide. The magnesium would bond to chlorine because it's positive and negative. And then the sodium would bond to oxygen because it's positive and negative. And then to summarize our very first video for Unit 1, I would love for you to pause this video, try to balance all these equations, and label them whether they are synthesis, decomposition, combustion, single replacement, or double replacement.